This video is going to give you some details about how drag works. Suppose we have an aircraft that's moving through the air. What forces act on the aircraft? Well, it's near the Earth, so the weight is the force of gravity pulling down. Because this aircraft has airfoils, there's lift, a force that pulls it up. There's also moving it through the air, thrust, the force forward, and impeding any acceleration forward is drag, the force of the fluid it's moving through, acting backwards on it. Notice something about this. If I superimpose in light blue here the direction of the streaming flow, the flow of fluid past the aircraft, there's a relationship between the thrust and drag and that streaming flow. Notice that if I change that direction, the weight continues to act down, but the drag is in the downstream direction, and it changes as I change the direction of the streaming flow. That streaming flow, again in the light blue, is from the aircraft's point of view. So the aircraft, imagine the aircraft perceiving itself at rest, and the flow of air going past it is going to be a backwards flow because the aircraft is moving forward relative to the Earth. So clearly one of the things that's confusing about drag is this dependence on direction. The drag is acting in the downstream direction. Lift, meanwhile, is acting in the direction perpendicular to that. So how does drag depend on other parameters? Right now, who cares? This is the expression for what we call Rayleigh drag, named for Lord Rayleigh, who came up with this expression, and it depends on several things, including the fluid density, the square of the flow speed, a drag coefficient, and the cross-sectional area of the aircraft going through the fluid. We're just going to take all the parameters that aren't the flow speed and call them K for today. So all of this stuff is K. So what do we have? We have the drag force is going to be proportional to the square, in this case, of the streaming velocity. That's the velocity of the air relative to the aircraft, times some coefficient of proportionality that just summarizes all the other effects. And technically, this is going to be negative relative to the direction of the flow. So it always acts to impede progress through the fluid. So that's the magnitude. It's going to be proportional to u squared. As you've seen in our earlier discussion, this could be equal to k times u to some other power, where n here, the power could be 3/2 or it could be 1. But in this video, I'm just going to consider the case where it's equal to 2. Notice that's simple enough, the magnitude, but the direction is what matters. So suppose I have u here representing the streaming velocity. You might be wondering, why am I using u and not v? Well, shortly you're going to see that we'll use v for volume, and I don't want to have confusion between volume and velocity, so we're just going to use u for velocity. So this vector represents the streaming velocity, and I know that the drag force is going to act in the same direction as that streaming velocity, but opposite. So whatever direction the aircraft's moving through the flow, the drag force is acting to impede that motion. Now, whenever we're describing direction, this great tool that we have is the vector. And one of the ways of describing vectors is by breaking them into Cartesian components. So I can break this u into a ux to the right and a uy acting vertically upward. If I add together those two components with vector addition, I'll get back the original vector. So something nice to notice here is if I break out u that way into those two components, x and y, then I can break the drag force into components along those same directions. And what does that look like? It looks like I have F, the drag force Fd, in the x direction here, and the drag force in the y direction there. And notice something about the angle here. This angle between ux and u itself is the same as the angle between the drag force and the x component of the drag force. So this angle here and this angle here, those are vertical angles, and they're equal angles. So if I can determine this angle, then I know the angle of the drag force as well. And all I have to do, taking that direction, is multiply by -1, and I'll get the drag direction. So how can we find that direction? Well, I can move these velocity components. Watch, I'll slide uy over to the right, and now I have ux on this, what we see as a right triangle, is the side adjacent to this angle. I'll call it phi. And uy is the opposite side. So I can come up with some trig functions here. I know that the opposite over the hypotenuse is going to be sine phi. So sine of phi is going to be uy over the magnitude of u. Cosine of phi will be ux over the magnitude of u. That's the adjacent over the hypotenuse. And tan phi will be the ratio uy, the opposite side, over ux, the adjacent side. Opposite over adjacent. So how can we use that? Well, looking at what we had before, I know that the magnitude of the drag force is going to be proportional to the magnitude of the streaming velocity squared. So I'm going to just take that magnitude of the force, that's represented by the length of this purple vector, and the x component will just be that quantity. And the same way we get the x component of any vector in this kind of coordinate system, I'm just going to multiply by the cosine of phi. And the cosine of phi, notice, is ux over u here. Where when I'm saying u, what I really mean is the magnitude of vector u, the length of this hypotenuse. So when you see this expression, this is just a way of getting the component of the unit vector that is pointing in the direction we're calling x from something whose total magnitude is proportional to u squared and equal to k u squared. Similarly, for f drag in the y direction, it's going to equal just magnitude now, k u squared times uy over the magnitude of u. And notice that uy over the magnitude of u is, again, sine of phi, where phi is this angle that we're using to reference the direction of both the velocity and, because we have our vertical angle over here, the direction of the drag force. How can we apply that further? We have these two components, so I know that my drag force here as a vector is going to be in magnitude minus k u squared, and then cosine phi, sine phi, and these two components here in the angle braces are just a vector telling us the direction of the velocity. Since we know that cosine squared phi plus sine squared phi is 1, we know that this is also a vector whose length is 1, or a unit vector. So how can we put this into the code? Well, first of all, how can we find phi? The way we find this angle phi is using the inverse tan or arctan function. The arctan is the angle whose tan is uy over ux. Arctan can always be read as the angle whose tangent is, and then the stuff in parentheses. And we know the tangent is opposite over adjacent, which is here the y component of u, over the x component of u. So, turning this into an algorithm, here are the steps. Find the angle phi using inverse tan or atan. That's step 1. Move on to step 2. Determine the acceleration based on the drag force. And we're just using Newton's second law here. I can find accelerations force by force here just looking at the drag force. A is the acceleration due to drag. That'll be equal to the force due to drag divided by the mass of the rocket. And this mass, don't forget, eventually will be changing in time, but in our code right now is just a constant. So we have the drag force, its components. We can find those components using that angle that we computed using inverse tan, and then we're using simple finite differences to update our velocity. So we can calculate the x component, say, of the drag force. It's minus k u squared cosine phi. And then Vx will be what Vx used to be, plus the acceleration. What am I doing here? It's a typo. F dx over m is the acceleration, and then we're multiplying by dt. We know acceleration is the change in velocity per time. We're multiplying by time, so that all together here gives us a change in velocity. So turning that algorithm into pseudocode, phi, that angle is a tan uy over ux. Then since ux squared plus uy squared is speed squared, and I'm computing the quadratic drag here, drag that depends on the square of the flow speed, I'm just making a variable called speed2 that means speed squared, and I don't have to do any fancy square root business here because I just want the square of the speed anyway. So f dx is going to be minus k speed squared cosine phi. Similarly, f dy is minus k speed squared sine phi. The acceleration will be two components. Ax is f dx over m, the drag force x component divided by m. Ay is the drag force y component divided by m. And we've already calculated the gravitational part of that acceleration in other parts of the code. So then I'm taking x, using basically my kinematic formula adapted to be a finite difference formula. X is what x used to be, plus ux dt, plus 1/2 at squared, a dt squared. And similarly for y, and we're going to update our velocities as well, again using v equals v plus at, or u equals u plus at in this case, since we're using u for velocity. So that's what the algorithm looks like in pseudocode. Find the angle, find the speed squared using the Pythagorean theorem, find the two components of the force due to drag, and we do that just using the sine and cosine of that angle that we computed using the velocity components. The acceleration is the force per mass, and then it's a simple case of kinematic finite difference equations to update the position and the velocity. So this is the screenshot you want to look at when you're looking at your Scratch code, and we will take a look at that next. I hope that's helpful.